Morning, everybody.
Morning.
Today I'll start with number 25. There was a question on that one. And then if you have any other questions after that, just let me know. I can go through those with you. So for 25, it's asking for the complete ionic and net ionic equations for each of the following reactions. For the first one, you have H3PO4. And these are all aqueous. Well, let's go just write them in, just be easier that way. Plus rubidium hydroxide. Oh, and that's aqueous too. And that goes to form water and rubidium phosphate. So they want the complete ionic equation and net. So when ions that are aqueous are in water, they separate metals from nonmetals. So for this one right here, rubidium hydroxide, rubidium's a metal. It will separate from the nonmetal area. So you're going to have Rb plus, and then the nonmetals will stay together. So whatever nonmetals you have at the end, you'll have as one unit, and that will form the hydroxide ion, OH minus. Now also there's a 3 in front of here, so you're going to have 3 Rb pluses and 3 OH minuses. And then over on this side, the same thing, metal separates from nonmetal, so you have Rb plus, and you'd have PO4 -3. Now that you can find on your polyatomic ion sheet, it's phosphate. If you forget the charge of phosphate, you could just go reverse and you can say, well, I know Rb is in column 1, that's a +1 charge, and there's 3 of them. So this overall is a +3 charge. That means phosphate has to be a -3 to cancel out the +3 charge. Now there's a 3 down here, which means you're going to have 3 Rb pluses. So you'd want to put a 3 in front of there to indicate that you have 3 Rb plus ions. Then water, it's liquid, and liquids don't separate. Anything that's solid, liquid, or gas will not separate in water. Only aqueous, because aqueous means dissolved in water. And when things are dissolved in water, they break apart into their ions. That's what that means. So that's why only aqueous is going to separate like this into plus and minus ions. Now for the first one, there's no metals right here. And so you might wonder what to do with this one, because like I said over here, metals separate from nonmetals. But remember we talked about this before, that hydrogen can act like a metal in certain cases. So even though it's not considered a metal, it will act like a metal. And it will separate from the rest. So we would show H separating from the PO4. Now, how do you know if that's a metal or not? Because over here, H is a non-metal. It doesn't separate. If it's in front, it acts like a metal. So if you have a hydrogen in front, it acts like a metal. If it's in somewhere not in the front, it's not a metal. Now you might wonder about over on the water side, then why does that not separate? That's because it's a liquid. So if it's an aqueous, then it would separate. H would separate from the O if it's an aqueous on here. But because it says liquid, then it will not separate. So only aqueous separates, and H will only separate if it's in front. So H will separate from the PO4, and it's like we have a non-metal H, or sorry, it's like we have a metal H with non-metal PO4. And then PO4 -3. And then we have H plus, and there's 3 H's, so we put a 3 in front of there. So now let's put it together and see what we have. So our equation would look like this, 3H plus, and these are all aqueous. Then we have a PO4 -3 aqueous, along with 3 RBs and 3 OHs. And that goes to form. So then we would have water. I'll write it down here. So again, it's liquid, so we don't separate it, so we just keep it as H2O. And then we have 3 RB pluses, aqueous, and PO4 -3, also aqueous. So what we have written right here, it would be the complete ionic equation. Now to do net, we would need to cancel out the ions on both sides. They're spectators. So all spectator ions are going to cancel out. So that would be the ones that are on both sides. Well, you can see right here, the PO4 is on both sides. So that would cancel out. And then the RB plus is on both sides. And then we would then just write down what we have left at that point. So after crossing out the spectators on both sides, we would have 3H plus aqueous reacting with 3OH minus, going to form 3H2O liquid. So that's the net equation. The other ones follow the same thing that I just showed you for this one. So it wouldn't be any different. You know, for C, you have H2S gas. And so again, just like with the liquid, that would not separate. But besides that, it's really the same rules that we talked about for this one. Any others you want me to go over? Any other questions you have either on this one or on other ones?
Actually, I have a question.
What question do you have, Sam?
On 36, I have a question on B.
Okay. So for 36B, so it says you have T1 is 37 degrees Celsius, P1, 5 atmospheres, P2, 2.5 atmospheres. They're asking to find T2. So we would need to use the equation that has all the things that we need. We have pressure and temperature. We use Gay-Lussac's law for that one, which says that P1 over T1 equals P2 over T2. All we need to do is plug in the values and we can solve. Just remember that with temperature, you have to have it in Kelvin. And so what we would need to do here would be to convert Celsius into Kelvin by adding 273. So the first step would be to do 37 plus 273 to get Kelvin. And then once we have that, we can solve. So that would give us 310 Kelvin. And now we can put everything in and go from there. So we'd have 5 atmospheres for P1 over 310 Kelvin for T1, P2, 2.5 atmospheres over T2. And the best thing to do at this point would be to cross multiply. So we would have 5 atmospheres times T2 equals 310 Kelvin times 2.5 atmospheres So let's see what that gets you. So if we do 310 times 2.5, it gives us 775. And that would be Kelvin times atmospheres for the units. Let me go ahead and erase the top part here so I can write this. Okay, so now our equation would be, get my cursor back on here, 5 atmospheres times T2 equals 775 Kelvin times atmospheres. Then we can just divide both sides by 5 atmospheres. And we can see that atmospheres would cancel out. We'd have Kelvin left. And so that would give us T2 in Kelvin. So we do 775 divided by 5. That would give us 155 Kelvin. Now with sig figs, we're only given 2 sig figs here. And so our answer has to have 2 as well. So we're going to actually round this up to 160 Kelvin for the answer. Anything else you want me to go over today?
Do we need to put it back in Celsius?
It doesn't ask to. So no, you don't have to. It didn't ask for it in Celsius. You can keep it in Kelvin.
Ms. Holly,
Yes.
I had a question on number 34.
Okay. Go through that one. So 34, the first thing you want to do is get grams. So we're given kilograms of aluminum. Multiply that out to get grams. So there are 1,000 grams in 1 kilogram. So that would give us 6.0 times 10 to the 8th grams of aluminum. The next step would always be to get moles if you have grams. So we'll convert that to moles. Aluminum's molar mass is 26.98. So for every 1 mole, you have 26.98 grams of aluminum. Divide that, we get 22,200,000 moles of aluminum. Now, what they're asking for in the problem is how much ammonium chloride, NH4Cl, is produced. So at this point, we would want to convert from moles of aluminum to moles of ammonium chloride, and then go from there. So we'll multiply the moles of aluminum by the molar ratio to convert to moles of ammonium chloride. So we look on the equation that we're given, we see that the ratio is 3 moles of ammonium chloride for every 8 moles of aluminum. Aluminum will cancel out, we're left with moles of ammonium chloride. So that gives us 8.33 times 10 to the 6 moles of ammonium chloride. And they're asking how much is produced, so they usually want grams. So we'll convert that to grams next. Look at the molar mass of ammonium chloride, it's 53.00 grams per mole. So that would give us 4.1 or 4.41 times 10 to the 8th grams of ammonium chloride. Any other questions you want me to go over today?
Miss Holly,
Yes.
for number 42,
Mhm.
isn't the coefficient already, doesn't that already stand for 2 liters?
So the coefficients can stand for several things, but yes, they can stand for liters as well. And so the ratio is, you can say is liters of H2O over liters of fluorine. Just write this really fast. So you could say, there's 2 moles of H2O for every 2 moles of fluorine, or you could say that there are 2 liters of H2O for every 2 liters of fluorine. So it'd be the same relationship. So you could take liters of fluorine, which you're given 2 liters, and multiply it by this ratio right here to convert to liters of H2O. And so it is exactly the same thing as using the mole ratio, it's just that we're going to use a different unit, but it would be 2 over 2. And so it'd be the same number of liters of H2O as liters of fluorine.
So because the molar ratio is 2 to 2, like everything would stay the same?
Yeah, for water, that's right. So you also would have 2 liters of water produced. Now, if they're asking about liters of HF, then that's different. So for water, you just get 2 liters of water. But for HF, it's a different molar ratio or different volume ratio. So converting to HF, you get 2 liters of fluorine to start with. So the ratio you'd use would be 4 liters of HF over 2 liters of F2. So you get 4 liters of HF produced.
Right, Miss Holly, but that's still the same thing as what they had in the original reaction.
Oh, I see what you're saying. So it just so happens because we start with 2 liters of fluorine, and that 2 is a coefficient of fluorine as well. That's why it happens that way. But if we were given a different volume of fluorine, then we wouldn't get the same number. So it only works this way because we start with 2 liters of fluorine, and there's a 2 in front of F2 in the equation. But this would work for any amount of volume. So if we instead had 1 liter of fluorine, and we're just told that's what we had, then what you'd have would be 1 liter of water produced. For every 1 liter of fluorine, you also have 1 liter of water. But for every 1 liter of fluorine, you'd have twice that of HF. So if you start with 1 liter of fluorine, you'd get 2 liters of HF produced. So it would be true for any amount of F2 you had. In this case, though, we were given 2 liters of F2, And that would follow the coefficients of the reaction because we have 2 in front of F2. Does that make sense?
Yes, ma'am. Thank you.
You're welcome. Okay, number 37. Let's see. So for number 37, it's asking, get my cursor back in here, I lost it for a second. There we go. Okay, for number 37, it's asking what mole will, or what volume will 0.875 moles of sulfur hexafluoride occupy at STP. So we're given the moles, and then STP stands for standard temperature and pressure. It's always going to be 273 Kelvin in 1 atmosphere. So by saying STP, we know automatically the temperature and the pressure. So we know 3 things. We know the moles, we know temperature, we know pressure. So we would need to look up an equation that gives us these things. Now, there's also a shortcut we could use. We could use Avogadro's law. Which says that at STP, which is what we said that we're at, 1 mole of any gas equals 22.4 liters. So that would be the easiest way to solve this. You know, we could use an equation or we could use Avogadro's law. And this was a lot easier way to solve it. So if that's our conversion, we can multiply 0.875 moles times that conversion factor and convert. So Avogadro's law says that for every 1 mole of gas, you have 22.4 liters. So we multiply moles times liters, and that would give us 19.6 liters. All right, number 32. So we're given grams of zinc and of manganese dioxide. Then for A, you want to find limiting reactant. So we would need to first convert grams to moles. So we have 25.0 grams of zinc. Zinc's molar mass is 65.38. So that gives us 0.382 moles of zinc. Then manganese dioxide, we have 30 grams. Its molar mass is 86.94 grams. So that gives us 0.345 moles. So we want to find limiting reactant, and we would need to know which one runs out first to determine that. So looking at the mole ratio in the problem, it says that for every 1 mole of zinc, we need 2 moles of manganese dioxide. So that's the requirements, that's the recipe. Now what do we actually have? So we have 0.382 moles of zinc, and we have 0.345 moles of manganese dioxide. So which one runs out first? Well, what this is telling us is that we would need double the amount of manganese dioxide that we have of zinc. So this to run completely, we would need 2 times 0.382. We would, but we don't have near that of manganese dioxide. So because we don't have twice the amount of MnO2 of zinc, then we know that this one has to run out first. So this is limiting because it runs out before the other one does. So manganese dioxide is limiting reactant because it is not twice the number of moles of zinc. And that would make zinc the excess. So there'll be some left over at the end of the reaction, which means we're going to base everything off of manganese dioxide. So for part B, when it's asking the mass of zinc hydroxide produced, we would use the moles of MnO2 to convert to moles of zinc hydroxide. So we'll go on to part B. So they're asking for moles of, or mass of zinc hydroxide produced. And we have 2 moles. We had moles of zinc, we had moles of manganese dioxide. We will always use moles that's limiting, that runs out first. So we'll use moles of MnO2. And we're going to convert to moles of zinc hydroxide using the molar ratio in the equation. For every 1 mole of zinc hydroxide, you need 2 moles of manganese dioxide. So that gives us 0.173. Now they're asking for the mass, so we can convert from moles to mass. The molar mass of zinc hydroxide is 99.42. And that gives us 17.2 grams. And then for part C, they're asking about the excess reactant. So we said before that zinc is in excess. How much is left over? To determine that, we have to use, again, limiting reactant to determine the moles needed of zinc. So we're going to convert from moles of MnO2 to moles of zinc. So using the molar ratio, we see in the equation, for every 1 mole of zinc, we need 2 moles of manganese dioxide. So that would give us 0.173 moles needed of zinc. Now, remember from part A, what we found is that we really have 0.382 moles of zinc available to us. That's what we started with. Do you have a question, Robert?
Yeah, so why wouldn't it be 0.382 moles of zinc? Because, or like, why would you need to multiply it by 1/2?
That's a good question. So that's actually what we need. So we have 0.382 moles of zinc available to us, but it's in excess. It's not all going to be used. We have more than we need. So once MnO2 runs out, zinc will be in excess, and you're going to have extra zinc left over. So we were given in the original equation for A, we know that we have 0.382 moles of zinc available to us, but we only will use up 0.173 moles of zinc. The rest will just be in excess because MnO2 will run out at that point. Does that make sense?
Yes, ma'am. Thank you.
You're welcome. So that's why we have to use this molar ratio here, because that tells us what we actually need in the equation. So what we have versus what we need, we subtract the two, and we get 0.209 moles remaining or in excess. So now at this point, we can convert from moles to mass. So if we have 0.209 moles remaining or in excess, and that's of zinc, we'll multiply it by its molar mass to go from moles to grams, 65.38 grams per 1 mole. That gives you 13.7 grams of zinc. Okay, there's a question about number 40, so we'll go through that one next. Right, number 40, it says calculate the number of moles of O2 gas held in a sealed 2-liter tank at 3.5 atmospheres, 25 degrees Celsius. How many moles would be in the tank if the temperature was raised to 49.0 degrees Celsius and the pressure remained constant? So we are given volume, pressure, temperature, and moles. So we have to use the ideal gas law, PV equals nRT. So the original pressure, 3.5 atmospheres, goes in for P. Volume is 2 liters. N is number of moles, that's the unknown, so we'll keep it as N. And then R is the gas constant. So it's always going to be 0.0821. The units are liters times atmospheres over moles times Kelvin. So the units are going to tell you what we have to use for pressure, volume, and temperature. In this case, we're just given the right units, but just, you know, you won't have in the test either. But make sure that you do have the right units on here and that they do correspond to the gas law constant. And then temperature, we can see it should be in Kelvin, but we're given temperature in Celsius, so 25 degrees Celsius. We'll have to add 273 to that to get it to Kelvin. Okay, so let's multiply the left-hand side, do 3.5 times 2. That gives us 7, with sig figs at 7.00 atmospheres times liters. The left-hand side, 0.0821 times 25 plus 273. That gives us N times 24.46. Actually 47. And then look at the units on here. So the unit for this temperature was Kelvin, and that will cancel out the Kelvin down there. So the units now would be liters times atmospheres over moles. Now we'll divide both sides by 24.47. You can see the atmospheres will cancel out, liters will cancel out. Do 7 divided by 24.47. We get 0.286. Now look at the units over here. You kind of mess what we did right there, but it would be 1 over a mole, which would be just a mole. If you remember, this would flip around and we would just get moles for our unit. So 0.286 moles is what N equals. So that's the original amount of moles. Then we have to change the the temperature. So we'll go back and change it. So all that's different is the temperature. So I'll leave everything else on here and just get rid of the temperature. So the new temperature they said is 49 degrees Celsius. So we'll just put that in right there. Everything else though stays the same. So 3.50 times 2, we get 7. And then on the right-hand side, 0.0821 times 49 plus 273. That gives us 26.4. And then again, Kelvin right here will cancel out. So now our units would be liters times atmospheres over moles. So we do 7 divided by 26.43. And that gives us 0.265. All right, so that's number 40.
Thank you.
You're welcome. Any other questions you want me to go over? All right, number 11. Let's see where that one is. All right, it says explain why calcium can form a Ca2 plus ion, but not a Ca3 plus ion. So looking at the periodic table, you look up calcium, it's in column 2. And what that means is that calcium has 2 valence electrons in its outer shell. So there's 2 options that it has. Calcium could gain 6 extra electrons to get a full shell, or calcium could just lose its 2 outer shell electrons. So if it were to gain 6 electrons, it would become Ca6 minus, because every electron is a -1 charge. If calcium were to just lose its 2 extra electrons, it would become Ca2 plus. So every loss of an electron gives it a +1 charge. So that's why normally calcium is a +2 charge. It's easier to lose 2 electrons than to get 6. And so it usually would choose to do this. And the question is, why is it not Ca3 plus? Well, if it was 3 plus, that means it lost 3 electrons. But that wouldn't make any sense, because at that point, it would be losing its core electrons. It's stable when it loses its 2 extra electrons. But if it lost 3 electrons, it would now be losing the electrons that make it stable. It would become very unstable at that point. So atoms choose to either get a full shell by gaining or losing electrons. And if they have 3 or less outer electrons, they're going to lose them. Now, aluminum has 3 outer shell electrons, and so it will become Al3 plus usually. But because calcium only has 2 extra electrons, it'll only become Ca2 plus and not Ca3 plus.